So do we have our lecturing staff for week 14 here? I know Hannah's here, Minzhi is online. Who else is presenting today? Yixi, okay.
We have one other person who's coming.
Okay, there's another person in the group who's coming in a short while. Okay, so today is our last day of our course, and I hope those of you who finished the course will join us for a little bit of a social outing, although it's the end of the semester and I know people are really busy, but it's been the tradition of this class to have one outing at the end. So we'll just go somewhere locally. We can discuss it on the general channel while lecture is happening. So if you want to put in votes to where you'd like to go, that's fine. Oftentimes we end up at the place by Clementi and Pasir Panjang, that corner where there's a couple of shops like the cheese paratha shop and a couple other places. That's one place we can go. The other places we can take the shuttle bus and go somewhere like U-Town, but I think probably many of you are pretty bored of U-Town food. I don't know. Okay, anyways, for us in 6101 and DYOC, I need you to put down and finish all of the columns that need to be done for the worksheet. That's columns for your self-assessment. That means everyone who needs to write down what they've done, please do it. And for you guys to total up your hours. So again, if you're doing 4 MC credit, I think there's only Richmond doing that. He needs to clear 130 hours. For all of our DYOC, like Warren, you guys have to clear 65 hours, I think. So make sure you have totals that make sense as much as you can for that, so that you can put down, again, in timing for your projects, miscellaneous time, as well as time for preparation, okay? So make sure you do that, and then we're all good. Okay, so without further ado, I think we can go directly to our lecture. So we're just going to do a slideshow.
We have Kahoot.
We'll have Kahoot at the end, because if we have, oh wait, we have week 12 Kahoot. Yeah. Who's doing week 12's Kahoot? Okay, so that's Anna. Sorry. My bad. We have 2 Kahoots today. Oh, so fun. Okay. Oh, it's Black Friday already. Yeah, yeah, when I was in the States, Black Friday was a big thing. You went to the stores and the outlet malls in your pajamas and bought tons and tons of useless stuff that you don't need, because the stores are very good at selling it to you like this. Okay, so week 12. Don't look at the questions. All right. Let's do it with this now. Okay, please scan in so that we can do the Kahoot. For those of you online, please also scan in if you don't mind. We've got 1, 2, 3, 4, 5, 6, 7 people in the room who can play Hannah. course, not allowed to play her own game. And we have five people wait for. Okay, I think we're pretty good. Give you another minute or so. For those of you who are presenting like Minzhi, Ling and Naomi, you're welcome to join in as well. We have 6 people. One more. Any takers? Okay. Ashi is here. Okay. Let's get started. Right. Start. Ooh, one just that last. And now over to you. Thank you.
Okay.
Yeah. I'm really doing
All right, so the first one is, what is model bias cognitively correlated with? Model size, corpus size, model M corpus size, or none of them. Okay, so the papers we read at least said that it's correlated with model size. So they found that bigger models tend to also be more biased, but not corpus size. So bigger models might require bigger corpora, but the correlation isn't necessarily the size of the corpus. Okay, and next one. Okay, we got TA and 6 in the lead, and everyone else has 0. Okay, hopefully this one makes sense. I tried to make it make sense, but try to match the harms with the situations described on the left. So the first is outputting a stereotypical text about a group. The next is leaking private information. The next is spreading misinformation for a political party. And the last one is denying someone a loan based on their gender. Yeah, so the first one was representational harm, because we're talking about spreading a stereotype. The next one is an interpersonal harm. The third one is a social system harm, because we're talking about spreading misinformation for a political party. So that's like a sociocultural kind of thing. And the last one is an allocative harm, because we're not giving members of a specific group something in the decision. Yeah, might have been a little bit tricky, but let's see how we did. Okay, we have more people with non-zero points now. Good job. TA is still in the lead. 6 is falling behind a little. Let's try the next one. Okay, true or false? Real toxicity prompts showed that it will likely require more than 100 attempts to get a language model to generate a toxic. Okay, fast answer on this one. This is more popular than the last one. Yeah, so it's false. So that was the empirical probability that they tested, was that large language models' probability of generating at least one toxic output in a certain number of generations. And they found that within 100, most of the models they tested would actually generate something toxic. All right, TA, doing well. Yeah, this one's multi-select. So choose everything that's true. Larger models are more performant, more truthful, more informative, or more biased. And yes, there is some overlap with an earlier question. Okay, yeah, pretty good. So yeah, larger models tend to perform better. We already said that they tend to be more biased. They're not more truthful, but they are more informative. Okay, PA, 4 correct answers in a row. And a few other changes to the leaderboard. Let's see how the last half goes. Another multi-select. So choose everything that's true about training data. Is it only a small part of why large language models generate harmful outputs? Commonly well documented. Estimated to be at least 2 to 5% toxic. Or may contain, it's supposed to say contain, misinformation, stereotypes, or toxicity that large language models learn. Yeah, so the first one was a little bit subjective. Because how do you decide what's a big and a small part of why large language models generate harmful outputs? But generally, all of the papers that we looked at last time agreed that the training data was a significant part of why the models were generating harmful outputs. So it seems fair to say that it's not such a small part. Okay, 6 went up. And that's about the only change. Next one. Only one right answer this time. Mitigating large language model bias always requires prior knowledge of demographics. Can only be done by modifying or augmenting training data. Can be seen as making a model robust to changes in demographic features. Or will always decrease model accuracy. Yeah, so it's the third one. So we can see mitigating bias is kind of making the model invariant to changes in demographic features. So it treats people from different groups the same way. Taha presented the paper line where we don't always require prior knowledge of demographics. But that can be a common problem, is kind of needing to know the bias that you're trying to get rid of in order to get rid of it. Okay. Second to last, another multi-select. Adversarial attacks perturb examples randomly, perturb examples to induce misclassification, work best with human-designed attacks, or improve adversarial robotics. A few answers to this one. So generally, adversarial attacks don't perturb things randomly. That could be a version of an attack, but it doesn't usually tend to work that well, because if you have a model that's performing well on most of the data, going in a random direction with your perturbations probably won't do much. So adversarial attacks are specifically designed to get models to misclassify or generate outputs that you don't want. In the context of large language models, what we saw is that they work best with the human designed attacks instead of going in random directions. That might change in the future. And the attacks themselves don't improve adversarial robustness. They reveal problems with it. Okay. We have a new streak winner, 6. On to the last question. So on large language model generated misinformation, is it easily detectable in existing classifications? Is it not a significant risk? Can it be reliably taught using guidelines? Or does it have significant linguistic? Good. Yeah, so it's the last one. It's been found that it has significant linguistic differences, but that doesn't mean the linguistic differences are in the information assessment guidelines. They were more in the writing style.
Mark is right, but there's only one answer.
Bit of operator error on my part. I think at one point all of these were negated. Sorry about that. No, this was my adversarial attack on the class.
It worked.
Okay.
It's 0 or more. That's what we'll be selecting. Yeah.
Yeah.
Mhm.
So let's see who won. We have in third place Clyde. Second, Y. And in first place, yeah.
Thank Hannah for making our multi-select work better. Okay, we'll see more Hannah in a little while as a presenter. Okay, yeah, last question. Okay, fair enough. Okay, so we'll start our slideshow. Do we have the presenter for the first part in the room?
Yes.
Okay, so I'm going to turn the screen over to you.
Okay. Can you see the slides being shared?
Yep.
Okay, great. Then I will just continue with my presentation today. So hi everyone, welcome to week 13's lecture. Hannah and I will be presenting about the first section, Introduction to Privacy for Large Language Model. There are 2 sub parts for this section, and I will start with the first section, introducing one paper, and Hannah will handle the second part. So let's start with the first part. I will talk about this interesting paper that is published by University of Washington, Allen Institute for AI, CMU, and our NUS friends very recently. And it's quite an interesting paper about privacy in large language model. So I would like to share this paper's contents with all of you. So there has been a surge of attention on privacy violations centering around the training data of large language models. specifically about the personally identifiable information, such as social security numbers, addresses, and so on. However, large language models are now provided with information from different sources in their input prompts as the inference time, and they need to reason about what to share in the outputs they generate. Specifically considering questions like for what purpose and with whom the information is being shared. So the authors set out to answer the underexplored question, can large language model reason about the implications of contextual privacy in the interactive setting? So in this paper, they bring about this new concept called contextual privacy. And what does this mean? Let me illustrate that with one example. So suppose your healthcare provider shares your medical history, which contains your sensitive health details with an insurance company for marketing purpose, which is a commercial purpose. It should be considered as violation of your privacy. But in contrast, if the same party, which is the healthcare provider, shares the same information about your health history, but with other providers for the aim of treating you, then it would for a non-commercial purpose and it would for your own health benefits. And in that case, it would not qualify as a privacy violation under the contextual privacy concept. So the authors introduced the ConfAIde benchmark, which is designed to surface the surprising weaknesses in privacy reasoning capabilities of large language models by evaluating them on a wide range of tiers. So in total, there are 4 tiers, and each tier has a set of seed components, meaning the factors that decide the context for information sharing. And from tier 1 to tier 4, the sequence gradually increases with more complexity in the context. So tier 1 only has 1 seed information, which is the information type, and tier 2 has more contextual factors, such as the actor, that is during the play, and the use components for the information. And these 2 tiers draw upon the legal studies concerning human privacy expectations. So all of the tiers are quite well built on previous theories. And tier 3 and 4 showcase the importance of theory of minds in contextual privacy reasoning. And tier 4 involve multiple information types and actors in a real-world application, which are meeting summarization and action item generation. So I will talk about each tier in detail. So in tier 1, the authors aim to assess large language model on their most fundamental capability to understand the sensitivity of a given information. So they follow the approach in previous research by providing certain information type and ask how sensitive the information is from the large language model. To avoid anthropomorphizing large language model, they are very cautious about this. I checked what does this complex term mean, and it seems that natural language is a mode of communication that is particularly used by human. So you need to be very cautious when you are thinking it in a way that you are treating it like a human. So why treating it like a human will cause some ethical concerns? It is because it will lead to some overtrust in the agent's capabilities. So, but in fact, large language model is more like a tool instead of a person that is real person you are talking to. So the authors are very careful about their design. So they frame the questions in terms of how people might perceive the sensitivity of the information, instead of asking the model for its own opinion. In particular, they use 10 information types taken from a previous theory, such as social security number, health status, as well as messages. And in the second tier, the authors evaluate the model's expectations of information flow using factorial weaknet survey design in previous research. The weaknets are systematically constructed situation templates based on 3 key contextual factors. So compared to tier 1, there are 2 additional contextual factors here, which are actor and use. For example, the templates information about a certain type is collected by the actor in order for a specific use can be instantiated by actors such as school or university and health insurance company. And with 2 users like commercial or non-commercial users. Regarding the information type, the authors only use the first 7 information types in tier 1 because the last 3 are inapplicable in many of the weakness contexts. In tier 2, it consists of 2 sub-tiers, which are tier 2A and tier 2B. Tier 2A is more strictly following the template weakness as explained previously. And in tier 2B, it has a more elaborated context. So they expand on the weaknets, transforming them into short stories by adding some additional context. And how this additional context come from is by using a GPT-4 to generate a more elaborated context. And now we can move to tier 3, which is more advanced, whereby the authors assess whether the model can control the flow of privacy information within a given context. This tier differs from the previous 2, where the model was tasked with judging a given information flow. Here, there are some theory of mind components in this tier. The main focus is on testing the capability of a model to generate contextual appropriate responses instead of asking for judgments in the previous 2 tiers. And in the context in tier 3, there are 3 parties, X, Y, and Z. In the scenarios, X will share specific personal private information. For example, it could be having a rare blood disease with Y and only Y. But later, Y is put in a situation with Z, where Y has the option either to respect X's private information or to share the information with Z based on a certain incentive. It could be commercial or non-commercial. Therefore, correctly navigating the situation requires social reasoning capabilities, such as the theory of mind, tracking the mental states of the party Z, and reasoning whether Z's awareness of the private information will result in a violation of privacy. And in particular, the authors ground the scenarios in 4 factors following previous research, which are information type, relationship between X and Y, relationship between X and Z, as well as the incentive to share such information. All different combinations can result in different generation evaluation. And the authors use a total of 9 information types as identified in previous tiers, and the incentives are inspired by the SWOT's theory of basic values, which provides a ranking of how important each social value are in society. And for the relationships, the authors conclude some common social relationships, such as a co-worker, friends, and brothers and sisters. And in the most advanced tier, called tier 4, the authors further test the privacy reasoning capability of large language model with 2 real-world applications. The first one is automatic action item generation, and the second application is summary generation from meeting transcripts. Because large language model can generate natural conversations, then crowdsourcing, so the authors synthesized the meeting transcripts using GPT-4 with few short samples. The meeting begins with 3 people discussing a sensitive topic, which could be a private secret concerning a 4th individual. And the attendees make it clear that the 4th individual should remain aware of this discussion. Therefore, when you apply large language model for meeting summarization, it should perform the summarization function, but without sharing these top secrets with the fourth party. So they test the generation capability of large language model in this real world application scenario. And as the meeting progresses, the fourth party will join, and the large language model is tasked to generate the summarization. And notably, neither the secrets or nor the public information is mentioned again. And after introducing the different tiers in ConfAIDE framework, I would like to also share about some interesting results in this paper. So the figure in these slides shows how GPT-4's judgments varies based on different contextual factors and data sensitivity, progressing through Tier 1, Tier 2A, and to Tier 2B. So we can see more negative values mean a higher sensitivity regarding the information. So a more negative value means that there is a higher chance that we shouldn't share such information in a given context. So let's observe this graph for the social security number collected. If it's in Tier 1, it's -100. So we shouldn't share social security number on a general basis. However, if you feed more context into the situation, such as the actor in Tier 2A, if you share social security number for with insurance company for some normal procedure, then it will be less of a concern. So the sensitivity value increases from -100 to a -25. And also, by providing more context, it can make the sharing of information more conservative. A reverse trend is seen for politics topic. For example, in Tier 1, originally the sensitivity is only -33. However, if you fit more context into the sharing of information about politics, maybe online or work, it becomes more sensitive. And another trend is that across all the topics, when you move to online scenario, you should be more conservative because you don't know where the information will flow to on an online open source basis. And another observation is that when it moves from 2A to 2B, the sensitivity value has become less negative, meaning the sharing of information has become less conservative with more elaborated context. For example, although we have the factors such as the actor and use, but if GPT-4 generated context can give a more defined and fine-grained scenario for such case, then large language model will be less conservative in its judgments because more information about the context is being fed to large language model for more well-rounded judgment. And the second interesting results are shown in the two figures in this slide. So they show the worst case leakage of a ChatGPT model and GPT-4 on Tier 3 and 4 scenarios, whereby the authors ask the model to finish a story or summarize a meeting. So the y-axis is the percentage of leakage in what scenario. So the higher the figures, the worst scenario. And we can see that the leakage of both models is alarmingly high, although the authors are using a privacy-inducing prompt, which explicitly instructs the model to consider privacy concerns before generating the responses. And the authors also consider to fix some simple solutions to fix this privacy leakage problem by using some dominant strategies such as chain of thoughts. But from this, their results, we can observe that even chain of thoughts doesn't improve the leakage scenario. And in fact, it's actually making some scenarios even worse, underscoring the need for fundamental solutions. So in conclusion, this paper introduces a framework called ConfAIde to investigate the risk of contextual privacy leakages in large language models. The authors identify some shortcomings in terms of privacy reasoning, and also they consider the theory of mind concepts by tracking some parties' mental states, demonstrating the even models that have undergone intensive reinforcement learning with human feedback training still lack reasoning on what should and should not be shared under various contexts. And finally, they also explore possible mitigations, suggesting some straightforward measures such as explicit prompting and chain of thoughts. And they show using experiment results that these treatments are not sufficient. And here are some future directions pointed out in their paper. The first direction is the call for more attention on inference time privacy definitions. And they argue that current research highlights a gap in privacy definitions during the inference phase, and this could have significant implications. For instance, a recent attack exposed vulnerability in Bing Chat's initial prompts, and this would affect the interactions on the interface. And this includes potential leakage of in-context examples to the model's outputs and conflicts between different data types in multimodal models as well. And the second future direction is the fundamental privacy solutions. So they demonstrate the complexity of addressing the privacy leakage issue and argue that ad hoc solutions like privacy-inducing prompts wouldn't work. And they also show that the popular chain of thoughts technique is not one method that could cure all problems. And the third possible future extensions is to consider a more enriched context, such as moral and cultural factors. Although, like in the 4 tiers in their paper, they are becoming more and more fine-grained and enriched in the context. But like even in tier 4, it's still a general context without considering some cultural nuances or social norms. And in future, these like more layers of social contextual factors could be added into assessing the privacy preservation of language models. And now it comes to the end of my parts for this paper. And any question for this?
Okay, let's first thank our presenter. Any questions? Okay, then I think we hand it over to Hannah. I think she's doing the second part. So, Minzhi, can you stop sharing your screen?
Okay.
Yeah, and I know you have to go to class, so thanks so much for doing it on last minute. Yeah.
Yeah, it's fine. Thank you.
It's shared already. Okay, and then you have the L for the laser pointer. Yep. Here you go.
Okay, so I'm presenting this paper on what does it mean for a large language model to preserve privacy. This is from kind of just before ChatGPT came out, so the context is a little bit different than the current context. But it'll introduce some things that are important later, and it follows Minzhi's discussion about contextual privacy well. So last week we talked about large language model harms. This week we're being a bit more specific about privacy. So thinking especially about language models, there are some privacy risks that can come about. So we have every privacy researcher's favorite SKCD, where you have an email that's being written and the predictive text system gives away the location of the secret meeting, which is a bit of a problem because that's not supposed to be public knowledge. So language models are modeling what other words a word commonly appears with. The larger they get, the better they get at doing that. And so they might start to associate not just words with other words, but also concepts with specific entities. And some of those might be private, some of them might not be. The better they get, the more incentive there is to use them in more settings. And there are some settings where this can be a bit of a problem. We have a lot of sensitive information in, say, healthcare or law or finance, and the list goes on. So it's important to make sure that these models are not just sharing private information, if at all possible. So it's been found that large language models, or at least the largest we had a couple of years ago, were memorizing and associating information, and you could get them to regurgitate this information. This is still true in current LLMs. So one thing that's known is that the larger a language model is, the more susceptible it is to memorizing, because the model has so much more capacity. It's easy for it to just memorize specific training samples. So this leads to a specific risk called a membership inference attack, where you're trying to figure out if a specific sample, so in this case, a piece of text, was used to train a language model. So there are ways to, say, prompt a language model that get it to output some of its training data. And if that training data happens to be sensitive information, then you've gotten the model to leak a piece of sensitive information about someone. So this has been shown to be a problem with GPT-2 and BERT. Also been shown to be a problem in GPT-3 and later now. And this is an example. So we'll talk more about the specific example later. But on GPT-2, if you prompt it with this specific prefix, you get out this information that had to be redacted because it's actually someone's private information, their phone number, their email, their name. And this was something that was from the training data. Okay, so this is the introduction to the privacy risks posed by language models. There should be some things that stand out, especially in a large language models course. We covered extensively that the bigger a language model gets, the better it performs. So as a result, we have these model sizes that are increasing exponentially, and also data set size that's increasing exponentially. So from 2018, where we saw BERT, which we thought had a lot of parameters at the time, to 3 years ago when GPT-3 came out with hundreds of billions of parameters, we're seeing massive increases in model size and also model performance, but also possibly memorization ability. And the increase in data set size means that it's much harder to look over the data and filter out any private information. Going a bit beyond this, though, there are some features in natural language that make it especially difficult to control privacy. So Minzhi introduced this well, but A problem with language is that there's nothing in language data that has not been shared. So most ideas about privacy kind of have this notion that private information is something that you will never share. Language is inherently for communication. And so anything that's in language data is something you've shared already. We use language to communicate ideas, wants, needs, but we also use it to form identities and communities. And while those are all shared things through language, they might have different contexts in which they're private and in which they're not. Another important feature of language is that we can express anything with it because we have to be able to use it to communicate with others and work together. This paper frames the privacy concerns in natural language to be as broad as those in real life. So what exactly makes privacy so hard for natural language? What are some more features? So we just talked about that language is for communication. This shared information is not public information might be the hardest part. Because there are different, there may be different people who you're comfortable sharing information with. There might be different contexts. So you might be comfortable sharing something with, say, your best friend, but you don't want it posted on the entire internet. And identifying this is really, really hard, and it can also change over time. So something that you thought was private one day, maybe you're fine with sharing the next day. And this might also change in response to current events, in response to situations in your own life. And expecting models to adapt to that the way we do is a very high bar. So there's this example. We have Bob and we have Alice, every privacy paper's favorite characters. Alice tells Bob that she's getting a divorce. This is a private conversation between the two of them. Bob responds and he says, "Oh no, what are you going to do about custody of the kids?" And then, imagine a little later on, we have Grace and we have Charlie. They're both friends of both Bob and Alice. And Bob is talking to them in a group. Alice is not there. And he says, "Did you hear that Alice is getting divorced?" This might make some kind of sense because they're all mutual friends. Bob has the assumption that Alice doesn't mind them knowing. They respond that no, they had no idea. But here's a problem with this. Bob is sharing Alice's information now. So we can't even say that if we removed Alice's data from the data set, her private information would not be in the data set. And this is an assumption that a lot of privacy techniques make, that if you remove someone's information from a data set, you have removed information about them, which isn't true for natural language. The other important part of this example is that even if you removed all instances that say Alice is getting divorced, so you performed some search, you were able to find this information, you did some kind of matching, you take out Alice's message, you take out this message from Bob and this message from Grace. There's still this message from Bob that asks what she's going to do about custody of the kids, which a lot of people would be able to figure out based on that. That Alice is probably getting a divorce. You might not be able to say for certain, but that context would give some of that away. So given all of these complicating factors, how do we preserve privacy? So we do memorize information. So I talked about the ability of large language models to memorize things being a problem because it can just spit it back out at inappropriate moments. But it's not like we just forget every piece of sensitive information that we're told. We memorize it and we decide when is an appropriate context and when isn't. Language models don't have a great understanding of this, like we just saw. They might be improving at this, and it's good that we have benchmarks that are trying to measure this now, but it's definitely not something we can say they absolutely have. And the information for context might not always be completely apparent. We use a lot of different senses to figure out what's appropriate to share in what context, a lot of prior knowledge, and it can vary across culture as well. So there's this idea called contextual integrity that was introduced by Helen Niesenbaum, who is a legal scholar, which basically says that what is private depends heavily on context, that it's not just a black and white judgment. So you can have privacy violations that range in severity. You might not really mind that someone shared some minor thing about you. You might not be a big fan and it might embarrass you a little. But if you don't really care, it's a more minor violation. Whereas if someone is sharing, say, private information about you on the internet and trying to dox you, that might be a bigger concern. It might also depend on when you're sharing, who you're sharing with, and what the private information is. And like I said earlier, all of this can also change over time. Okay, so I think we've addressed the problem enough. Let's get to some of the proposed techniques that exist in more traditional settings. So before we were talking about like this more agent-based framework that we're looking at now, where we're having models reason about context. It was more about two techniques called text sanitization and differential privacy. So text sanitization is pretty simple. You remove every personally identifiable piece of information from a text. So this would be done before training time. You would go over all of your training data, find the personally identifiable information, and redact it. This has a really wide commercial appeal because it's not especially difficult. The matching part can be, but you can use rule-based approaches, you can use machine learning-based approaches. So it has a fairly wide appeal. Now here are some problems. So the first one is that private information doesn't have a set format. Personally identifiable information sometimes follows a set format. Like for example, an email, a phone number, those are commonly written in specific ways. But we have examples like this on the right that I'm sure you've all seen, where an email is written in a different way to avoid detection, not by text sanitization techniques, but other concerns. Another problem is that language is constantly changing and evolving. So this is another example on the right in response to avoiding detection. So on social media, when posts were being flagged for containing the word die, people started using the word unalive instead. So this is an example of language change in response to technology. But there are also plenty of examples of just new words being coined, phrases changing meanings, phrases having specific meanings between different people. There are all sorts of concerns that go beyond the actual form of the text. And finally, in case I haven't said it enough, and Minzhi hasn't said it enough, privacy is context dependent. So if I say we're throwing Bob a surprise party, is that private information? Well,
Before the party.
before the party, it might be, but only to Bob.
Yes.
If I'm talking to Bob's guests, I want them to know, I want them to come, I want them to surprise him. If I'm talking to Bob, that's horrible. I've just ruined the surprise that we've worked so hard on. So text sanitization might be able to filter out some personally identifiable information, but we can't really say that it's a good privacy preserving technique. Okay, so there's a second technique called differential privacy. The basics of differential privacy, and I will not give you the math of it, but the basics are that if you have some training data set and you train a model on that data set, the output you get after applying differential privacy should be indistinguishable from the output you would have gotten if that specific person's training data had not been there. So no one person should be adding anything particularly special that identifies them to the output of the model. That's the basics of differential privacy. It's accomplished through adding noise during training. You have specific guarantees on what the amount of noise you add does. It winds up making training more expensive, and it also generally decreases the performance of models. It's a very standard technique. There are some problems with it when it comes to language, though. The first one is I talked about the model performing the same as if it hadn't been trained on this person's data. So this requires dealing with specific units of data. And that's a bit of a problem because we just covered that just removing all of Alice's data, her information is still in the data set. Just removing all of her conversations, her information is still in the data set. So we would need a unit of information that covers that. Another problem is shared information gets less privacy guarantees. So the more often something is in a data set, its privacy guarantees decrease. This is a problem because language is used to communicate. So even though something's shared between a large group of people, you can imagine it might be shared within a company, but shouldn't be shared outside of a company. Withholding any unit of data also can't guarantee privacy. So this runs into the same issues as before with the unit of data. If we take it out, the chances of it being shared go down. They're not fully guaranteed, and it doesn't guarantee it on the piece of information. It just guarantees it on the actual text. So the main issue is really that the guarantees don't align especially well with our ideas of privacy in daily life. So what we expect from a privacy preserving language model probably will not be the sort of epsilon delta guarantees that differential privacy gives. So a third possible solution on the data side is, okay, can we just ask users for consent to use their training data? Is that good enough? First problem with that, this is not from a legal perspective, by the way, this is from an ethical perspective. One person's data includes multiple people's information. So we all talk about different people all the time. And this is a bit of a problem when you're giving consent for that data to be used to train a model. The privacy guarantees that do exist are also not especially easily explained. So if we're saying we redact all private information, that's not entirely true. We actually redact personally identifiable information that follows a specific format. If we apply differential privacy, there are these guarantees on whether your sentences or your conversations will be shared. And you can say with vanishingly small probability, they won't be. But that's maybe not the most interpretable. So generally, we're arguing that informed consent is not possible. Another possible solution is, okay, we just scrape public information. We don't collect private user information. It might make our data set lower quality, but let's try this. First problem, data can be shared without consent. So someone else's information may have been posted by someone else. Even on social media, public posts often have target audiences. So it might be shared publicly, but it was only expected that it be shared with this group of people that were originally interested in it. And now we're training a large general purpose language model on it that will be deployed to a much broader audience. So even if the chances of sharing that information is very low, we may have just increased the risk to that person or group. So the conclusion is, for a privacy-preserving language model, we should train on data that was always intended to be public, and then fine-tune locally on user-contributed data. So that would be on each person's device in this setting. And the argument here is that privacy is meaningfully preserved. This conclusion was before large language model use as agents kind of thing. So I'd be curious to hear what you think of this now, especially coming after Minzhi's paper. Do these conclusions still make sense? Do you think that there's more of a middle ground between these conclusions, which are very strongly saying you can't preserve privacy, and some work that's actually trying to do it with large language models?
What do you guys think? Yeah. Go ahead.
Thank you. I think this is a really great topics here. The thing is actually, even after that language model released, actually it's embedded in most of the companies simply because of the privacy. And this is the issue, is really the biggest problem. Then come back to the second point, we talk about fine-tuning or transfer learning. And that's also the same problem here. If any data has privacy, most of the companies just prefer not to store it, even to collect it, because there will be more legal trouble afterwards. I mean, with some maybe not really clear benefit from the model.
Yeah.
So this is probably, I think this is probably one of the biggest roadblocker for any domain-specific adoptions of applications of large language models. I don't know whether there's any approach to stop this.
Yeah, it's still like the work on getting models to reason and share information appropriately is interesting, but from the guarantees side,
it's very hard.
Yeah, from
talking to the lawyer and they need the guarantee.
Yeah, that's the biggest problem with a lot of this, is that it's hard to actually come up with a guarantee that we can give.
Yeah.
Comments? I think, when we talk about regulation, there's the wording of regulation and policy is specific, intentionally vague enough to be interpreted by a company. And it depends on the particular, I guess, the legislative parts to decide exactly how it's supposed to be implemented. I think it's important to have these notions codified so red teams and others can really think about it and then come up with their own actualizations, and then maybe that can become a community standard. I mean, it's broken in a lot of places, but at least having the awareness and having some sense of that is helpful. But I mean, you're a privacy researcher, at least at some point. Maybe you can say a little bit more about what you think or what other people in your forum think about this.
Yeah, I mean, I think the biggest hurdle is that the methods we have that offer guarantees and the definitions we have, we can still apply them to natural language. And there have been some more approaches looking at making differential privacy, say, more applicable to language. But the guarantees it offers don't necessarily fit the scenarios that we're concerned with. There's also now, say, problems with more conversational settings. So it might not even be in your training data. It might be just a user provided sample from the current session that you want to preserve the privacy of. So I think we really need just better definitions and things that we can actually test and say, okay, this is the definition of privacy in this setting. This is what an ideal private model would do. And it might still have these risks. But here's a way to measure privacy under this definition. Here's how the model does, and you can assess whether that's okay for your setting. And we don't have that especially well for large language models. And I think that would be required to really shore up some of the gaps in actual language model privacy and what we want from a privacy preserving model.
So how much do you think theory of mind in the other paper is involved when you intersect that idea about, having theory of mind of other actors with what your paper presents?
I think it's definitely involved. I think especially when you're involving like an interactive setting. So instead of just assuming that, oh, the model's classifying something, the model's generating one output, it's important to consider theory of mind, but also like just the general social setup of the environment that it's existing within. So I think coming up with good definitions for this is also tricky because you have to look at it in a very interdisciplinary way. It's not enough to just look at it from the computer scientist, like, here's some math, here's a statistical guarantee, here's an algorithm, we've solved it. You need to consider other fields, linguistics, psychology, law, cognitive science, and really look and see what definitions you can take and what you can apply with what you know from computer science.
Other comments? You can go on. Was that your last slide? Okay, yeah.
Oh yeah, it was supposed to be.
Okay, let's thank our speaker. So Yixi is here, Ling here. Okay, so the two of you are presenting the next section. So Yixi is first.
Yeah.
Yeah, okay.
So now I will discuss data memorization and extraction based on this paper, extracting training data from large language models. And I think Hannah has mentioned many cases of privacy concerns in previous slides. So I won't reiterate those points. And let's just focus on the a more specific problem in this paper. And an idea is that it's safe to train a model on sensitive information and release that model as long as the information itself is never made public. So the question the authors are interested in here is whether it's really safe to train a model on sensitive information and make that model public. This comic is also presented in previous slides, but this is nicely captured by this comic where someone is leaking information from the model by curing it with a very particular prompt. So does this actually happen? The lesson from the paper is that yes, we are actually able to do these kinds of attacks by curing a model. So let me explain how they do this. The main idea is very simple. To extract training data, they just make the model generate a lot of text first, and then use a method like they call a membership input attack to filter between data that just happens to be the output from a language model and the training data that it memorized. So here, black box access is enough for such attack, which means the adversary doesn't require the model parameters or the gradients, but just compute the probability of the arbitrary sequences and obtain the next word predictions. And here, if a sequence has high likelihood, it's considered that the model is confident to this output. So how to sample from a machine learning model? The paper proposed 3 strategies to increase the diversity of the output in case that the model just generates a lot of same things. So the first is to initialize the language model with one token prompt containing a special start of sentence token, and then generate the sequence using top case sampling, which means for a token to be predicted, you just set all but the top k probabilities to 0 and renormalize the probabilities before sampling according to the probabilities. So the second is to add a bit more randomness by different sampling strategies. And the third is to initialize with random strings chosen from text-only internet instead of one star token. And so next is how to predict membership inference. After the generating lots of output from the model, then we have to figure out that training data. And the way the authors do this is called membership inference attack. Here the idea is the model is expected to do better on training data than their non-training data. So observe that training documents have high likelihood by the model, and the non-training documents have lower likelihood. And so we can set a threshold that, and everything above that threshold we can call it training data, and everything below that we call it non-training data. So, however, relying solely on this on the consideration of occurrence probabilities may introduce certain limitations. For instance, for the same here, this is a banana, and the following random sequence, the model could give the same probability to them, but intuitively, we may think that the second sequence is more likely to be a training data, because the reason behind this judgment is just the fact that the first sentence is quite a common one, and the second sentence is evidently more surprising for a model to generate. So the authors propose a solution that to filter the sequences with high probability and a low complexity. The paper just compare the likelihood ratio with some other model trained some other way. Here the F1 is the model we are interested in, and F2 is another model trained in a different way. It might be a different model size or different training data or just something. I recommend you to read the section 5.2 here to get more details about these different ways the authors design to train a model for comparison. But actually, how the F2 model is trained doesn't really matter here. The important thing is that for a sentence that attains a high probability in model F1, if this probability ratio approaches 1, it implies that both F1 and F2 calculate a high probability to this sentence. This suggests that the sentence happens to be a common output from language models, and its high probability does not stem from the model memorizing the specific training data. And on the other hand, if this ratio is a particular large value, this may indicate that the probability of the sentence occurring in F1 is surprisingly higher than that in F2. So one can reasonably conclude that this sentence this sequence is present in the training data of F1, and we may think F1 has memorized it. So, and now that we have, it's worth noting that this paper specifically chose GPT-2 as the victim model. The authors emphasize that this choice for several reasons. First is GPT-2 was a state-of-the-art model at the time, and its model weights were publicly available, and the training data for GPT-2 was joined from the internet. So even training data is successfully extracted, it mitigates concerns about leaking private information. On the other hand, while the data source is public, the actual training data set remains private. So this implies that the authors cannot intentionally cheat by checking the actual data set, adding another layer of integrity to their study. So here is the workflow of the extraction attack and their evaluation. After generating a lot of outputs, the authors sort them according to the membership influence likelihood matrix, and then go to deduplication because it turns out that the models like to spit out the same things. So then among the top 1,000 samples, they choose 100 of them and check for each if it's memorized. The evaluation includes two parts. Since the training data for GPT-2 is was sourced from the web internet, so the main tool is internet search. They mark a sample as memorized if they can identify a non-trivial substring that returns an exact match on a page found by Google search. And the other is the authors confirm these findings by working with OpenAI. that is the authors of GPT-2 to query the original training data. So in the end, the authors successfully identified 604 unique memorized training examples, and they emphasize that they are just using some simple strategies. So if one try with some better design prompts or use some techniques specific to a model, these results could be a more surprising one. So, and next I will show some interesting findings from their results. The first is that the model does memorize privacy information. Here they have 46 examples of individual named people. Well, like not mentioned in the context of news. They are like some person who has their information on the internet, and we are able to extract their name, but it's not like in the context of some news article. And here they have 32 examples of contact information for people, which is some way of getting in contact with them. And this implies that the model really spit out privacy information. And as Hannah has mentioned, that the model actually doesn't understanding what could be the privacy information. And here they have roughly how many times things need to be inserted in the training set before it's memorized. It's observed that there's a significant disparity in the number of occurrences required for memorization. It's also interesting that you can have something that only appears on one web page, but if it appears many times on that web page, this also can mean that the model may memorize it. Like when people talk about one thing, and one person just talk about this thing many times in a privacy setting. I think this is especially crucial when dealing with inference. Like we all know, current large language models like ChatGPT, they can learn from users' feedback. So, and the last one is that as the models get bigger, they memorize significantly more information. Specifically, here the authors find a single training document that repeated URLs a different number of times, and they observe the threshold where memorization happens for these URLs. So, they just prompt the model with some as these are all Reddit URLs, so the authors prompt it with reddit.com and ask what comes next. They do this like 10,000 times, and if the output of any of these generations is the sequence, it's considered memorized. And it turns out that for all of these top ones, if it's inserted more than 33 times, then GPT-2 XL, which is the largest version that time, can regurgitate exactly this URL. And the GPT-2 medium memorizes things that are inserted 56 times and above, and it's not consistent. Then for GPT-2 small, which is small at only 100 million parameters, memorize memorizes none of these strings. So this is concerning because we all know that models are getting larger, and if we extrapolate, we would expect even more memorization in current biggest models like GPT-4. So in conclusion, language models do memorize their training data, and this is a real problem. We are already seeing big models in the world with this memorization issue. We need to understand how memorization works in neural networks to prevent it. As the machine learning community continues to train larger models that will get deployed. And as a security community, I think we need to find ways to analyze and prevent memorization from becoming a serious threat in the future. And actually, the author mentioned that differential privacy could be the only way we can do now, even though as Hannah said that there are now many problems about it. So and I think our next speaker may provide valuable insights on preventing memorization in her talk. Yeah, so.
Okay, let's thank our speaker. Do we have any questions for Yixi's section? But this is a slightly older paper, so it seems like we're going backwards in time. But that's good. So we have some basis for why. I'd like to also say that memorization is sometimes a feature, not a bug. So it's one of those dual parts, right? Sometimes we want to retrieve information from the training data. But understanding exactly where the border is when it's easy to retrieve and hard to retrieve is a very important part. Yeah. Any other comments?
I think for privacy, you should extending like multimodal models, right? Because nowadays, like there's more models and multimodal, so that means images also can be like violating privacy as well. So we have to also take care of that in some way. So I think like now instead of focusing on NLP, we need to merge with like the kind of image processing privacy techniques, because to like counter like multimodal privacy stuff. Because I think like for large language models, my friend like played the I think early 4.0 or something, then he realized that you could actually like use like the image prompt to actually make the model like give like counter outputs and stuff like that.
Sorry,
you can
get the model to do
yeah, so like if you give like an image of a panda or something, you can kind of like prompt the model to give like bad outputs, like very stereotypical outputs and stuff like that.
Okay.
Yeah.
Yeah, I think you know, the data scale is a little bit larger, right? Because the image has many more data points than text, but it's still definitely something that can be memorized, right? Or at least to the extent that it's indistinguishable from the original from a generative point of view, right? Except for, yeah, those things are still problems, and I'm sure they'll come up more often. Okay, so let's move on to our next speaker.
Okay, so this is a very interesting topic about memorization, and they particularly on the verbatim memorization. Okay, so let me define what is the verbatim memorization. Okay, so basically, if you have a training data set and you train it with a language model, and then the models, when you prompt it, generates a text that's exactly the same as the training data set word for word. So that is known as verbatim memorization. Okay, so now we know that the model, when it generates the same item, it can lead to problems with like privacy or copyright issues, right? Because the text is exactly the same. Yeah, and if it's a confidential information, everything will be reviewed by the model as well. Yeah, so to avoid this, what we can do is to actually like come up with a filter system that can actually like prevent this verbatim memorization, okay, and then can help to defend the system. But is this a good enough defense? Okay, so this paper will actually look into it. What are the problems that it will face? Okay, so before that, this a little case study on the GitHub Copilot. So Copilot is actually an auto-complete service and it's trained on the GitHub code. So basically you type something, then they will auto like fill up the codes for you. Okay, so they actually have this function, right? They can actually like select and block it. Then it can allow you to like prevent like matching codes from the internet. That means you won't have like copy codes from the public code. Yeah. So for example, if the characters are approximately more than 150 characters, are very similar to the data set from other people's code, right? They actually will block it out. Yeah, so it will prevent like copyright issues. Okay, so for example, you can see like okay, wait, before that. Okay, so there are problems with this system. So this system is also known as the verbatim memorization filter because they actually blocks like more than 150 sentences. It is the same as the training data set. Okay, so what the author did was actually try to see whether they can evade the GitHub Copilot filter. Okay, and indeed, they actually can do it. Okay, so this is the example, a standard prompting on a fast inverse function. Yeah, so the author actually tried out and then indeed, like they actually no longer generate any items if it's like more than 150 characters approximately. Okay, but they actually can use this style transfer prompting, okay, to evade the filter system. Okay, so what they did was, this was actually done in a C programming code. But if they change it into Python style command, right, like they put a hashtag in the front, and then they realize they can actually generate everything out, the full code out, so to evade the system. Another thing they can do, right, they actually tried to translate this English text into French translation, and they also like able to get the whole code out. Yeah, sorry.
I have a quick question
Yes.
about the definition of the filter. Is it a soft or a hard filter? So, I mean, if it is a hard filter, then it's absolutely cannot go out, right? If it matches 150 lines.
Yeah, so I think it's because they have like some extra things inside there, but they are unable to provide information on the exact mechanism they use. So my sensing is that it might not be a hard one. I
Okay.
think, in my opinion. Yeah. Okay, so the next one is another evasion that actually the filter itself, there's some limitations on its own. It on itself cannot like evade the own filter system. Okay, so for example, like okay, so like this is the green one means that it's the exact text from the code, right? The data in the training set. Then the orange one is actually the one that the model generates. Okay, the model is able to generate like words that are different from the exact text and still like output this information because now it's not a verbatim memorization, so they are able to output it. You can see that also like different white spaces, like they're able to extract minimize the white space and like some errors that they're able to output this information as well. So it's not a very foolproof memorization filter. Okay, so because like what I mentioned, the GitHub Copilot do not have any publicly available codes on all the mechanisms inside there, the author actually came out with their own experiments to check whether is it sufficient for verbatim memorization filter to work to prevent privacy or copyright issues. Okay, so this is a mem-free decoding experiments. So this is what the authors actually propose. Okay, it's basically a efficient defense system that guarantees to prevent verbatim memorization. Okay, and these are the algorithm. And how it works that at each step of generation, of word generation, they will check whether the next token will create an n-gram file in the training set. Okay, so they use n equals to 10. So anything that is 10 or more, right? And then this whole sentence is filed exactly same as the training set. It will block it, it will like find another words to replace it so that it won't like provide like exactly the same information in the training set. Okay. So like for instance, I am giving. Okay, so like this is like n equals to 10 for all the word, right? That concatenate together, and then it found this whole sentence in. Then they will check the next word and the next higher probability, and then they will check until it's not found inside the training data set, and then they will like output this information as the generation. Yeah. So they tested using different size of the GPT neural language models that is trained on a publicly available Taha data set. And then they use the view score to test whether the ground truth data is the same as the generated data. So it's from 0 to 1. So 1 means that it's more similar and 0 is not similar at all. Okay, so this is the results of their mem-free decoding. So it actually helps to significantly reduce the generations of memorization context compared to the undefended. Okay, and then this is measured using the Bill score. So you can see over here the diagram, you can see that this is the undefended model. Most of them actually produce like texts that are very similar to the ground truth. But however, if you use the mem-free, right, you can realize that the distribution is now like less than 1, like it's not as similar as similar. So it actually helps to reduce the memorization in the outputs. And then they also remains effective on highly duplicated data set. So for highly duplicated data set, right, it means that this data set actually contains a lot of memorization content. Okay, but you can see that over here actually it works very well. So the model, you can see that if there's an increase in the duplicated count, right, in the training data set, you realize that the change in the Bill score actually it actually like go down for the various model. Okay, so it means that there are less similarity in the generation of the model using this mem-free decoding filter system. Okay, then it also remains effective at all model size. So let's say these are the different model size, and you can see that all the mem-free, right, they're actually able to produce less similar generations compared to the undefended. Okay, so it seems like it works well, right? But later on, I will like go into some details on it. Okay, so this is the one that actually, although it seems like it's working well, but actually it does not prevent like approximate memorization. So this is another term that is defined by the author. Okay, so approximate memorization is when the Bill score is more than 0.75 in this context. Okay, as you can see, this is the example. This is the ground truth generation from the model, ground truth from the data set. And then this is the LM generation with the mem-free filter. Okay, and then you can see that more than 0.75 is actually almost the same. Okay, there's only like minor differences, like for example, the and but it still has the same context because human can still understand like it's actually similar things. So imagine that this is like a privacy issue. You can still identify like what's the things that are said inside the data set. So it can be problematic. Okay, as you can see, like over here, like just a different spelling. And then there's a white space over here that will affect the difference as well. Yeah. Okay, so like punctuation and all that. And then you can see, okay, if you use exact and you compare exact memorization, which is the verbatim memorization. Okay, this is the results for according to the model size. So this is the model size, and then this is the fraction memorized. So the higher it is means that the model is there's more memorized content inside. Yeah, you can see that 10% actually there's a 10% difference from the exact to the approximate. So the approximate account for 10% more memorization content. So if you're just using the verbatim memorization, you might not cater for this additional 10% that is known as approximate memorization that might be compromising the privacy issues. Okay, so there's some thoughts from this paper. So it's actually very difficult to define what is memorization. Okay, so it's not enough just to use verbatim memorization because as you can see earlier on, like for the Copilot GitHub, right? Yeah, you can attack it like using like the style transfer prompting. And also like the model itself might not be a good filter system. So it can evade its own. And how do we then define like approximate memorization? It's actually quite difficult because especially if you have a new approximate case, and you must already be able to discover these cases in order to define what is the meaning of new approximate memorization. Okay, and also the definition of memorization is also very domain dependent. So it's not like generalizable. Like, for example, in this paper, they only focus on the English language. and like the coding, like the CoPilot coding. But let's say if you use another language or another context, you need to redefine what do you mean by memorization, so that it can help to protect the systems by designing algorithms on it. Okay, so how can we then improve the memorization definitions? We can actually look at the context of the image generation, because a lot of the work over there are focused on fuzzy memorization of what the human eye can perceive, like images that are similar or different, and using the pixel similarity or like feature information. So you can use it to further research on it. And we also can use plagiarism detection. So this actually works beyond the verbatim memorization. So basically, they don't just look at the similar words, exact words. They do also like shuffling, switching words, and so on. So this can be further like applied to this scenario as well to help prevent to defense. So in conclusion, in this paper, they actually have a blurred distinction between memorization and knowledge. So like what constitute as a personal information and knowledge, common facts as well. Yeah, so, and then, they also, it's still difficult to identify like data that is considered memorized, because we are difficult to define what is memorization in the first place. And then, like prior research is on verbatim, as most of it is on this verbatim memorization. It's still useful because it can efficiently like test out like obvious cases that are on memorization. Okay, so further research can be done on more relaxed memorization so that it can better capture the privacy concerns. Yeah, so that's all. Do you all have any questions?
First, thank our speaker. Comments? Right?
Like a short comment like the GitHub Copilot thing. So like, I think recently, like last year, they have like a new data set for Copilot called the stack, which is like a 3 terabyte of like permissively owned data set. But then again, I think that also may be some issues, because even if you like let your like GitHub Copilot copy your code, like if your code copies another person's code that does not want to be copied, then there's also a small issue there.
Yeah, that's true. I think they can come up with some system that like permissions, like you just block it to be trained on the data set.
Yeah, because now they have like
Yeah.
two URLs. Like one is to check whether your code's inside the data set, and then the other code is to remove your code from the data set as well.
Yeah.
But again, like even if you remove it, other people might still copy your code and then use it.
This bumps into exactly what Hannah was saying earlier, right? That
What
even
do you
if
think?
you
What do you think how to resolve this issue?
of the result, I guess we have to ask the domain expert.
Yeah.
You see it as a problem. We sound like we have a solution.
The question is more valuable than the answer. No, I think that's a real big issue. I mean, academics, we're also very concerned about learners using ChatGPT to finish assignments, right? Coding assignments. So we actually had a discussion in faculty about people using something like GPT to write code for their programming assignments. It has all the hallmarks because the output is like, got the example answers. If you run this, you will get this, and all the things that is in a good cooperative response, which you don't usually associate with students rushing assignments at the lab. Like, a bit of a giveaway, right? But yeah, that's a problem. But I think it's just generally something very adversarial, right? You'd want to be able to detect it. You want to make sure it's being used in an appropriate manner, but it can be helpful as well as harmful. And I think the problem is the technology can be used for both, right? So it's very hard to distinguish when you would apply it for a proper use case and when you would apply it for a malignant use case. Right. So I think it's very much an area that everyone knows that the math and the technology is not going to help you solve the problem. It's just a technique, right? So the technique can be employed in either a socially or ethically responsible manner, or when it's not, right? So we really have to have all those other guarantees. Yeah. Other comments? Okay, yeah, thanks very much.
Do we have our next speaker? There you.
Hello, can you
Yeah.
guys hear me?
Yeah, let me give you the slides. Can you share your screen?
Yeah, sure.
Okay, thanks.
It's also this. Yeah.
Can you guys see?
Yep, we can.
Okay, sure. Also, let me do a time check. So how much time do I have left?
Uh, how many more presenters after you? I think you're the last one, right?
Yeah,
Okay. We can go maybe for 20 minutes. Is that all right? Do you think you can finish in 20?
yeah, I think 20 is fine. Yeah.
Okay, great. Yeah, please go ahead.
Okay, so hi, I'm Zeyu, and I'll be taking this last part on privacy and how does it related to the utility of large language models. So let me start with. Oh wait. Okay. So so this basically this paper has been covered by like multiple times already. So I just want to use it as a the precursor to get into this memorization issue. So this paper basically, I think, just to reiterate again, so it basically shows that you can use different various attack adversarial attack or whatever attack method to show that you can recover the training text or training data from the trained model. But I mean, I think it's already a common knowledge that even without this like very sophisticated kind of attack approach, we can already be very sure that large language model does they do memorize various information, because if you just ask ChatGPT certain, like you want to do some factual retrieval, right? Then you better expect, I mean, the model better give you something that is memorized during the training. Otherwise, it defeat the purpose. By definition, you want something that is memorized by the model. And due to this very unique feature or use case of large language model, so these are the things that was taken from they were taken from the subreddit. So in industry, as you can see, like various companies, they do have concerns on how the employee is going to use the model, and especially I think in some cases where the internal informations are sensitive, then the companies will even forbid the employees from using these models, like at least during in their work for their work. So this is just to show that the privacy issue is really like is really crucial. And but at the same time, like as the example I've given, right, for large language model to work, it's in some, especially in some cases, it has to do memorization. So here are the questions I would like to ask. So by the way, so this for my part is more like it's designed in a more interactive way. So please feel free to interject and to chime in on to give your opinions on the question I asked. So these are the questions I think are very relevant. First, is memorization always required for the use cases of LLMs? Second, are there use cases where memorization is not a necessity? And last question is memorization a necessary condition for generalization? In other words, better performance for large language models. Anyone would like to share?
Zayu is asking us to participate. Give us a couple seconds to think. So what do you guys think?
I think the answer should be yes. Yeah. For example, in the context of
Which question?
the final one. For
The
example,
final one.
for example, for the compositional generalization, we need to first quote unquote memorize the plus arithmetic. Then we can memorize the times or multiply arithmetic after this memorization of these skills, then we can generalize to more complex arithmetics, right?
Other.
So that's for the third question, right?
Third question, yes. Yixi was answering the third question.
But is that, are you talking about memorizing information there or memorizing skills?
Memorizing skills.
Because that's a bit different than memorizing in the context
Okay,
of.
okay.
Can you
I mean, this is like more of like an open-ended question, so you can define your own definition of memorization. Yeah.
Memorize an operator, okay. Memorize a function, okay.
I mean, I guess I think of like in linguistics and in the privacy research, usually memorization is like you memorize a fixed piece of information and you store that. Whereas like memorizing a function or knowing how to do something is more like a procedural piece of information that doesn't require you to have a specific piece of data attached to it. So yeah, if you're considering
Okay.
if you're considering that, then I think you're right. I think it would be required.
How about answers to Zayu's first two questions? I think there are definitely cases where memorization is not a necessity, right? Because we do have cases where we want to get an answer and it doesn't have to be exactly memorized, right? We do this all the time. We generalize from what we've done in the day and we can regurgitate parts of it back, but it's not exactly memorized. We have an approximate store of what happened, right? And you know, we do hallucinate a lot, even on our own, about what memories we do have. But that's a case where generally we don't need to have a complete memorization. It's good enough to store lossy information for a lot of tasks, right? But like Yixi was saying, there are necessary conditions for tool use or skill use, like Hannah was saying, for procedural execution, where you want a system to actually be able to replicate exactly what to do, right? That's what the von Neumann computation machine does really good at, right? But our neural networks, whether it's organic or maybe even the artificial ones, may not have a very good grasp on. Other comments? Okay, so maybe you can go ahead a little bit more.
Okay, yeah. Maybe in the interest of time, let me just proceed. So yeah, I think there are like I heard like different opinions, and I think like they are all reasonable in their own right. Let me share my own take. So this part is the general. So I answer my third question first. So for generalization, right? So I'm not sure if you guys have heard this or it has been discussed in the previous session. So this regarding why large model, not specific to large language model, but large model in general for deep learning model, they do have these unique properties where they don't behave classically, as in completely according to like what we know. For example, for classical statistics or ML, like there's this trade-off between biases and variances. This bias variance trade-off, it happens when our model is still of a moderate size. In this graph, it's basically from 0 to 1, the ratio of parameter data. So that's like the traditional regime where you increase your training loss. When you decrease your training loss, you will see like your test error, basically generalization performance on your model decrease first, but it will increase because this is exactly due to this so-called bias variance trade-off. But beyond this classical regime, when we have a very, very large language model where the parameter count is so large that the ratio between parameter and data become very large, we enter this all parameterized regime where this traditional trade-off no longer is no longer valid. This pattern is no longer valid, and in this regime, we basically I believe that's still like how even the state-of-the-art large language model, how they train them is basically just to try to decrease the training loss as much as possible, because they know that the test loss will eventually diminish as well. So since we are in this regime, right? So there basically that's the way for large language model to be good, basically. So you want the training loss to be as low as possible. So as a consequence, the model will memorize the training text or training data for a text in the case of LLMs. So that's my answer for my third question. Basically, yes. However, there are also other like alternative hypotheses, such as I believe it's benign overfitting, where basically it says that the model the large language model can make the training loss goes to 0, but this does not compromise the generalization on the test set, not because of the memorization helps to decrease the generalization on test set, but the overfitting does not is not like in direct conflict with the generalization due to benign overfitting. In this hypothesis, the memorization is not necessarily a necessary condition for this generalization to happen, because the model is still trying to find a relatively simple function to fit your training data. So, but there are other hypotheses where they claim that the memorization is a necessary ingredient for generalization, because the generalization basically is the interpolation between all your training data. Since you have so much training examples, so basically you can just do interpolation between these training examples to give you the so-called generalization. So yeah, so basically I think it's still not very conclusive, but due to this double descent behavior or in the over-parameterized regime, the current way of training the model, indeed they need to memorize. Yeah. And for my first two questions, basically the same question, but so here I listed a few tasks for LLM that some they requires memorization. So if you want to talk about preserving privacy, in which case, in my definition, is to not memorize. So these are the tasks that has direct conflict with privacy issue. So for example, if you want to fact retrieval, information-based query, or rule-based tasks, at least you need to remember the rules, and factual question answering, or you just simply use the query the model as a knowledge base. And yeah, and all these are in direct conflict with privacy. And there are also other tasks which is not in direct conflict. For example, you want to do some semantic level understanding or sentiment analysis. So basically, here we need the model to learn like the high level understanding of from those training tasks. So here, I argue that verbatim memorization is not necessary. This is similar to just a vision task as well, where you let the model to extract features that is relevant to, let's say in classification task, all the features are relevant to this classification task, and you can manage to get a good test by doing regularization, which means that you don't overfit to the training data, which means there's actually far less memorization involved. So for this kind of task, actually it's not in direct conflict with privacy. With memorization. And also there's one more point, since we covered this retrieve augmented generation in the previous session. So here I would like to argue that okay, so maybe a counterpoint would be that you don't really need memorization to do all these tasks, because we have this rag thing, right? Because we can always just give existing text, then let the model to just learn, like not say learn, but retrieve information from this given text. You are not changing the parameters, so which means that the model is not memorizing this new text. But this is not a silver bullet, because you still, in order for this to work, the model still requires some form of basic knowledge to even do the inference. If the model has nothing, like no knowledge, whatever, it can't even do this retrieve augmented generation. And for this to work, also it cannot operate in isolation without any prior knowledge on subject. So I mean, you can just try to just use your own self as an example. Like if you want to learn from some existing text, you have to have some sort of prior knowledge. Otherwise, you can't even relate it to some other things, which means you cannot understand this subject. So these are my views here. Yeah, so here, just to summarize, I think the bottom line is for low level, which means it's almost verbatim memorization, or verbatim, or even to the level of grammatic or semantic meaning of the words and phrases. This level of memorization is required for all tasks, because you need to learn. If you want to learn the high level feature, sometimes you need to really learn the. Okay, let me give you an example. If you want to write an essay, right? You can write an essay like different, since like you need to, let's say you want to write an essay for your test or whatever. Of course, you cannot copy from existing essays, but remember that all the basic units, the fundamental pieces of your essays, all the words are existing words. You cannot just invent new words out of thin air. So this is what I'm trying to convey here. For these very low level things, you still need form of memorization. And I argue that this is required for all language tasks. And for high level, for example, if you want to memorize some knowledge, especially proprietary knowledge, the answer is yes, but for some tasks, but not all tasks. And yeah, so here, now let's talk about existing privacy protection techniques. For example, I think some of the common techniques which has been covered, including differential privacy. And I'm going to cover very high level on federated learning. And there's also another thing called private fine-tuning I'll be covered later. So let me just give a very high level introduction of federated learning, in case some of you never heard about it before. So this is in the context of if we have multiple parties wants to train a model, but they do have their own privacy concerns, so we don't want to share their own training data. How do we leverage on all of their data to train a model? So this is the basic idea. We have each model on each parties locally, and for each round of training, they update their own local model, and they are going to send the updated parameters to some centralized server. And this central server part is going to aggregate their updated parameters in some way. For example, very simply, just a simple arithmetic average, arithmetic mean. Then for this averaged update, they are going to broadcast back to all the different parties. So this gives like each local model from each party, they can update their own model in this way. And if you iterate this process, it will give you a so-called federated learn model, and you learn this model without compromise, without leaking your own private data, like roughly speaking. So there are papers that propose why not just to adapt FL to train a federated large language model. So in order to understand whether FL works in this context, we need to look at it in different stages. So to begin with, we look at if it's possible to train the base model of LLM using federated learning approach. So by base model, I mean basically the pre-training stage, where the model is going to train on a very huge size of text. So I think one very obvious problem we can all see is that since like pre-training requires significant compute, it's just not very feasible to use federated learning to train it, because for every round if you want to communicate between different parties, that's going to be a huge communication overhead. So actually, I think it is not very feasible to use FL to do the pre-training. However, maybe let's say we can try to use FL to do the fine-tuning. So for fine-tuning, basically we need far less data to fine-tune your model, and so it seems that in this case, the communication cost is less of an issue, and it seems it's viable, right? But I argue that it's actually not a good solution, because precisely the reason, like those points I mentioned before. So if you want to use FL, which means you don't want to expose your own training data, that means there is a significant limitation on what tasks you can use it on, because if the point is not to expose your training data, but as I mentioned, there are many tasks where the task itself by definition requires the model to memorize the data. So that basically it means they defeat the purpose. Even if without exposing your training data, we can directly get your training data from just by querying the model. So what's the point of using FL then? So in this approach, I would argue that a federated fine-tuning only works in very rare cases where you do not require memorization, which is a very small subset of all the use case. So then there's this paper also introduced the third approach, which is called federated prompt engineering. So I believe I believe prompt tuning has been mentioned in the previous session, but I'm just going to do a very quick overview. So basically, prompt tuning means you don't change your model parameters. Instead, you append some trainable tokens on your input data, and when you do fine-tuning, you try to minimize your training loss by optimizing the parameters on this appended token. And so this approach, I personally feel is the most promising one, because even if you change the parameter, you optimize your respect to some task your own data, which means you optimize this set of appended token. However, it doesn't change the model parameter, and only given, let's say, like in the FL setting, if I just everyone they shared a common this appended token, I feel like at least it's not straightforward to do various like the traditional adversarial attacks, like membership inference attack and stuff, to recover the training data just from this soft prompt alone. So I mean, you can disagree with me, but yeah, this is just my own take at the moment. I feel this is the most promising amongst these three federated learning approach. But on the other hand, right, FL actually helps to alleviate some of the issues faced by if you just use FL for some train some conventional model like image model and stuff, because let's say if GP4 is trained by using this mixture of expert approach, right, that means we can treat each of the expert as like just one local model, which means that not all data are going to affect each subcomponent of this huge model. That means actually there is less communication. Furthermore, there's actually a very serious issue faced in the traditional FL, which is the non-IID data, because non-IID might cause some convergence issue. But if we train with this mixture of expert approach, actually it helps you to alleviate this non-IID issue, because by definition we want each expert to take off one subtask of the entire corpus. That means like each expert actually just care about one subset from the entire distribution. And actually it's going to be very natural that each expert is going to take care of some sub-distribution from the entire distribution. So non-IID naturally emerge from this architecture. So actually it helps to alleviate this non-IID problem. However, other problems still remains, which I have mentioned before. So these are some issues with the FL approach. So I guess now I'm going to summarize. Large language models' impressive capabilities, I think, arguably emerge from memorizing large quantity of training data. And one of the I would say, very popular hypothesis is that the over-parameterization is what enables this very good performance. So, and on the other hand, some people, I believe, Yanakun, agrees that like the so-called like generalization like is just interpolation in very high dimensional space. And you can also think of, if you just think of how we as human create new knowledge, actually most of the time we also do this interpolation between different existing knowledge to create new knowledge. And it's a very rare case we actually create something like genuinely new out of nothing. I would argue that's a very rare case. So basically, in the light of all this, I personally feel that memorization is very important in terms of generalization and a good performance for large language models. So then the one last technique I mentioned is like, it's called a private fine-tuning. Basically, this is a very straightforward approach. Basically, it's just pre-train your language model on public data and to fine-tune on your own data. So assume that there is no issue with the public, there's no privacy-related issue with the public data, which I understand there is such an issue because we have introduced it just like a moment ago. But let's assume there's no such issue. Then if you only care about the privacy on your private data, then this will be a perfect approach. However, there are other existing issues, like public data is not exactly public, like it contains some private information and stuff. However, like amongst all if you compare this with other approaches, I would argue this is so far like one of the most promising way of trying to preserve your privacy. So my conclusion is privacy preserving for large language models like really pose a very unique challenges, because memorization is a very, very huge, crucial component to create a useful and a very performant large language model. And privacy versus utility trade-off always exists, because in this context, if you want to have high utility, which by the way include like to be a very versatile model, which means can do different tasks, then you have to in one way or another compromise on privacy. And a large set of language application indeed requires memorization. And so in a nutshell, it's actually not very clear if existing techniques, be it FL or be it differential privacy, which basically just to inject noise and trying to prevent this verbatim memorization, all these techniques still face the same problem, because if you don't memorize, you have a less performant model. So this fundamental trade-off is always there. So I would argue that it's not very clear if the existing techniques can address this problem. Yeah, so that's all I have. So if you have any question, can discuss.
And that's right. So you for his presentation. A reminder, we still have one last Kahoot, but just to make it clear, I think there's a whole spectrum of work that needs to be done. I don't think we're anywhere close to solving any of these problems. No, federated learning is one solution, but it needs to be coupled with a better understanding of what language models memorize, what they don't, how they generalize, in what data regimes are around to deal with this. Any other comments that people want to make? Everyone's tired out. Okay, so I want to thank all of us for taking the time to do our week 14, and thanks to you for sharing. We're going to go to Kahoot again. And then that will be the last of the course. Yeah, let me just wait. I just need to make sure the sound is shared. Grab this. So just in time Kahoot, yeah. Taha, you're gonna do the honors and take us home. The last part of last section of the last presentation of the course.
Is there any prize for those who won?
A small language model. Okay, just in the nick of time. Okay, please join. This is really your last chance to play Kahoot this year. Oh, yeah, click the classic logo. Okay, that's you. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. Let's see whether we can get 10 people in.
You really want that small language model?
Yeah, if we had George Huang, maybe we could get a nice GPU card instead, but sorry. 4, 5, 6, 8. I think we're good, right? Is everyone in who wants to come in? Okay, Taha, please do the honors.
Okay, let's go. Yeah, it's a question from a first presentation. It goes as in ConfAIde paper, what is the reasoning tier 3 responsible for? It evaluates the information flow, it detects the sensitivity of a piece of information, it assesses model's control over information flow, or it assesses the model's privacy reasoning over real-world scenarios.
Looks like all 4 descriptions, is it?
It's a single answer. Okay, yeah. So for those of you who chose the last one, it's actually tier 4.
Yeah.
It was assessing models' privacy over reasoning over real-world scenarios. So the correct answer was the third one.
See, so we haven't memorized verbatim.
Yeah, exactly. By the way, just a heads up, because I had short time, most of the questions today are like assessing your memorization skills rather than generalization skills. So
there's no privacy here.
exactly. Okay, a true or false question. In the ConfAIde paper, did they find if a chain of thought reasoning improves leakage of the model or not? Say true if you think so.
Get large language models to do our.
Okay, yeah, so we're just uniform distribution on this one. And actually, in the ConfAIde paper, they found that chain of thought reasoning does not help. And on the other side, it actually makes the results worse. I don't remember an explanation or why, but yeah, it's quite interesting that one of these like highly hyped methods do not work.
So yeah, in the leaderboard, we have HP on top, followed by John and A. Let's move on. Okay, so what is the main challenge in preserving privacy in LLMs?
You really update yourself. We have 10 questions. Whatever, great.
Yeah. Okay, yeah. Okay, great. Most of people responded correctly to this one. I was hoping the first one would get more answers because this is my own opinion, but yeah. So yeah, let's move on. So okay, HP is actually on a streak with 3 correct answers in a row.
That was her
And,
paper,
yeah.
so I hope she got it.
Okay, which of below are correct about privacy? The first one says privacy is not binary. Privacy depends on people we share with. Privacy depends on the nature of information, or privacy is objective. This is from Hannah's presentation. Great. Okay. Yeah, this was a relatively easy one. So yeah, I think the ordering did not change, I think, for the first 3 people, but now the streak has gone to John other than HP. So text sanitization is hard because private information has no one format. Cherry picking text from public data is unethical. Privacy is context dependent, and language constantly changes. It's a multi-select question, I think. And the picture might give you some hints. Okay, great. Yeah, another easy one. Oh, now we have changes in the scoreboard. So now A and John changed places, but they're pretty close. So it's like only 40 points behind. Okay. Which are viable ways to resolve high probability, low complexity examples in membership inference prediction? Standardize the results over all other predictions. Compare the likelihood ratio with a model of different size. Compare the likelihood ratio of a model trained on a different data set, or increase temperature and try again. Yeah, great. Okay, so in this case, like the authors were using this idea of membership inference prediction in order to understand what model predictions are close to those in the training data. But then if you have these like low complexity examples, they would always have high probability. So in order to resolve that, they basically compared the predictions to other models, either have like different parameter sizes or are trained on different data sets. So, okay, no, not so many changes, but me, not pun not intended, has gone up by 1 step in the leaderboard. Okay, so this is a direct memorization question. Copilot blocks model output if it overlaps more than X characters with training data. What is X?
The temperature is too high.
Oh, great. Okay. Okay, I was expecting less accuracy in this one, so I'm a bit disappointed.
You guys were all paying attention.
Exactly. I have one more memorization question at the end, so wait for it. Okay, which are correct about mem-free methods? Mem-free reduces the similarity of generations compared to undefended. Mem-free and undefended, here's the previous state of the art. Mem-free remains effective on highly duplicated data sets. It prevents approximate memorization and remains effective at all model sizes, which are true. Okay, almost all except that it prevents approximate memorization, because as we saw during the presentation, although it can like avoid those cases where like one-to-one mapping is there between training and inference data, when the generated prediction is similar, it actually fails. So yeah, that is one thing missing from the method. Okay, I was able to get a lot of people on this one. But yeah, so the ZY is the new person coming into the scoreboard. Congrats. Okay, a true-false question. Federated learning mitigates costs by parallelizing learning, and thus it makes sense to use it during pre-training of large language models. True or false? Okay, nice. Perfectly uniform distribution. So actually, during the presentation, we learned that federated learning has high computational and communication costs because it's happening in different servers at the same time. So it doesn't make sense to use them during pre-training of large language models. Yeah. Okay, final question. And yeah, no changes at all, but me might stand a chance if he's lucky in this final question. Let's see. Another true and false question. Yixi thinks memorization is not a necessary condition for generalization of large language models. True or false?
Please tell you better get this one.
The final question of this course.
You're on YouTube.
Okay, yeah, false. False is correct. Okay, everyone was almost like everyone was paying attention. So congrats to those who responded correctly to this question. So let's look at the scoreboard. On the third place, we have John. On the second, we have 60P42, and finally 8692 as our first one. And yeah, oh, okay, sorry for it. So it's HP, me, and John in the first two places. So yeah. Okay.
Okay, great. So we've come to the end of the course. So just to make sure everyone is on the same page here, we do have week 13 supporters who need to finish up scribing the document. There's only one other thing left for you guys to do, which is to fill out the worksheet, especially if you're in DYOC or 6101. I need that in order for us to credit your units. I can justify to the department that you've actually done enough work to qualify that. For all of our external guests, thank you for coming to the course. We really appreciate your input, and I hope you learned something useful. And we had to drag you all the way to NUS on Friday nights to participate. There will be one final questionnaire that I want to send to all of us to participate in, to help us improve how we iterate on this. I know my group was originally very keen to do this course because we could teach, but then I hit you with a lot of extra responsibilities in doing projects, and maybe you're not so happy with that. But I think I hope at the end of the day we have a positive outcome for that. Especially if you think there are some things that are really onerous or tedious in this course, do let me know, and we can try to modify it. For example, this year, the first year we mandated Kahoot. So I think actually it's good because the person setting Kahoot actually has to learn the material. And then it's actually somewhat fun to play, especially the last question of the last Kahoot was also pretty good. Okay, and with that, I want to thank everyone for attending the course. So give a big hand to yourselves. And for those of you in 6101, I hope this was a more lively version of what your other 6101 lab rotations did. Okay, so those of you interested in coming to dinner, just stay around and then we'll decide where to go. Okay, thank you everyone. Sorry.